When we were up at the Mount Washington Observatory, we saw several pitot tubes that were used for wind velocity measurement. Now, the pitot tube is commonly used for airspeed measurement both in wind tunnels and on aircraft. And what I'd like to do now is go back to MIT to one of the wind tunnels to see how a pitot tube works, and then go out to the MIT flight test facility to look at the mounting of a pitot tube on one of the flight test aircraft. I'm standing in the test section of one of the wind tunnels at MIT where students conduct a variety of experiments such as testing the aerodynamic performance of airfoils or sometimes measuring the drag of bicyclists or skiers. Now, you can probably see that the wind is coming over my shoulder and sort of blowing through this open jet test section. And the wind's blowing about 40 to 50 miles an hour right here. Now I'll step out of the airstream. And I'm going to shut off the tunnel here. When we make measurements in the wind tunnel, we need to know the wind velocity very accurately in order to be able to use the measurements that we get. Now, in order to do that, we typically use a pitot tube. And the way the pitot tube works is it measures the difference in pressure between the front of the tube and the side of the tube. You can see there's a small hole here which goes to a connection at the bottom of the tube. In fact, the static measurement goes to this other connection. Now, as this is exposed to the flow, what happens is that the pressure in the front of the tube, what we call the total pressure, is higher than the side pressure, and that difference is proportional to the square of the flow velocity. We've seen pitot tubes used for flow measurement at the Mount Washington Observatory, but we can also use a pitot tube to measure the velocity or airspeed of an airplane. In this particular application, you can see that the pitot tube, which measures dynamic pressure at the head, is located slightly away from the body of the aircraft so that it's cleanly exposed to the flow. In addition, this particular pitot tube is heated so that if the airplane flies through icing conditions, say, the probe will remain clear. Another phenomena that I can use to measure flow velocity is convective cooling. An old sailing trick is to lick your finger to measure the flow velocity. And the principle here is that the air blowing by my finger causes evaporation, which I can feel as cooling on my finger. Now, the same principle is used in hot wire anemometry or hot film anemometry. And we'll go back to the wind tunnel at MIT to look at this technique. Another method we can use to measure flow velocity is by looking at the effect that the airflow has on cooling or the thermal properties of a probe. So this is an example of what we call a hot wire probe. And basically the way it works is the air flowing by this thin element at a constant temperature by running current through it. And by knowing the calibration of the device, we can infer what the flow velocity is by how much current we need to put into the element to keep it at a constant temperature. Now, these are very sensitive devices. I have another one here hooked up to this meter, and you can see that just my breath can cause it to sensitive scale of full-scale deflection. So we can take the probe and actually put it into the airflow, which is running fairly slowly here, and you can see that I get a fairly accurate measurement. And you can see that it responds fairly quickly when I take it out of the flow. The speed of response will depend on the size of the wire. A very fine wire will have a fast response, but will also be very fragile and tend to break if the flow is too high or if it hits a little piece of dust or something like that. Often we can learn much about flow by just visualizing the direction of the flow or flow patterns. Sailors often tell a lot about the wind just by looking at the ripples in the water. There are many different techniques for flow visualization, and what I'd like to do now is just go back to the wind tunnel at MIT to look at just a few. In addition to knowing the velocity of a flow, we're often interested in knowing the direction of the flow or some other aspects of the flow. So for example, we'll use a smoke wand to see how the air flows around this airfoil, and you can see that near the tip we get rotation in the flow due to what we call a wingtip vortex. And as I go through here, you can see turbulence which is created by the flap there. Another flow visualization technique is to tuff the airfoil or body that you're interested in. So in this case, we put these red tufts on the airfoil, and you can see that the flow is fairly clean and going straight back on the airfoil. Now, as I increase the angle of attack of the airfoil, you can now see that the flow doesn't go over the airfoil very cleanly, and we have what we call separation or turbulent flow. Okay. As I reduce the angle of attack of the airfoil, you can see that the flow smooths out again. So this is another flow visualization technique that we use. One of the most sophisticated techniques for both visualizing and measuring complex flow patterns is the laser Doppler velocimeter, or LDV. I've come here to the water tunnel in the MIT Ocean Engineering Department to look at a two-component LDV system. Right now, the tunnel is set up to look at the flow patterns in the wake of a propeller. And the water tunnel pushes water in this direction, and you can see that the LDV is set up behind the propeller. Now, there are two sets of beams here. You can see a blue set of beams and a green set of beams. The blue beams are set up to measure flow in the horizontal direction, or the mean direction of flow in the tunnel. And the green set of beams are set up to measure the component of flow in the vertical direction. The actual measurement point is where all the beams intersect. You can see the beams cross here. And the laser can be moved in, out, up, and down to adjust the measurement location behind the propeller. Now, to show you how an LDV works, what I'm going to do is shut off the green set of beams and just look at the horizontal measurement. The laser Doppler velocimetry technique is similar to the acoustic technique we talked about a little while ago. However, this time, instead of scattering sound waves, particles in the flow scatter light from the lasers. Now, recall that the Doppler effect is caused by motion of a source or scatterer, and as this source approaches the receiver, the Doppler shift will cause an increase in the frequency. As the source moves away from the receiver, the Doppler effect will cause a decrease in frequency. And so what we do, if you look at the two beams here, we have one beam which is looking slightly upstream into the flow, and another beam which is looking slightly downstream. The upstream beam will see particles approaching it, and scattered light will have an increase in frequency. The downstream beam will see particles going away from it, and will have a slight decrease in frequency. What we actually do in this heterodyne system, which means we're comparing the two scattered light beams, is that we compare the upshifted frequency from one light source with the downshifted frequency from the other light source. And as the velocity increases, the shift in frequencies will increase also. So we have a very sensitive way to measure velocity. Before I show you the processed LDV data, I wanted to show you the raw data coming in from the laser system. If you look at this oscilloscope, you can see the output from the photodetector